All right, geometry class, let's go over our last lesson in this chapter. And this will be lesson 11.9, guided practice, where we're going to find scale factors of solids. We are familiar already with finding scale factors of two-dimensional figures. We're now going to extend that to three-dimensional figures. So starting with guided practice 1, is the pair of right solids shown similar? And then explain. So we're given two rectangular prisms, and I have marked what we would consider the width, length, and height of both of these rectangular prisms. And we're asked to decide if they're similar. If they are, all of their edges will be in proportion to each other. That is the corresponding edges. So that is width 1 to width 2, length 1 to length 2, height 1 to height 2. When we compare those sides of each of the rectangular prism, they would reduce down to the same lowest terms ratio. So let's see if that works. So for our width 1 to width 2, 12 to 9, that reduces down to 4/3. If we compare the length of our first figure, 16, to the length of the second figure, 12, 16 to 12, that also reduces down to 4/3. And then comparing the height of 4 to the height of 3, so that is our height 1 to our height 2, again, reduces down to 4/3. It is 4/3. So all of the ratios of the corresponding sides are the same, therefore those two solids are similar. What about guided practice 2, this cone? Are those similar figures? Now keeping in mind that when we're talking similar figures, whether they're two or three-dimensional, we're talking the same shape but a different size. So we want to make sure that all of our sides, all of our edges are in proportion to each other so that the shape would be preserved, that it would be the same whether or not we enlarge it or reduce it. All right, so for this cone, height 1 to height 2, that would be 15 to 10. That reduces down to 3/2. And then writing the corresponding ratios from the first figure to the second figure, that would be 10 to 5, and that reduces down to 2/1. So these cones wouldn't be similar. They wouldn't be the same shape because the corresponding dimensions in the cone are not in the same ratio. 3/2 is not the same thing as 2/1. We do need to check the lowest terms, the fully reduced ratio, because sometimes it might look like the ratios are different, but once we reduce them, they could very easily end up being the same. For example, if we had a ratio 6/8, would that be the same as the ratio 3/4? And the answer is yes, since 6/8 reduces down to 3/4. So always be sure to reduce your ratios when you are checking to see if they are the same or not. All right, now we're going to move into the theorem that kind of sums up what we were just doing. The similar solids theorem says similar solids with a scale factor of a to b will have corresponding areas that compare a squared to b squared and corresponding volumes that compare a cubed to b cubed. And that makes sense because there will be two dimensions that will correspond and will be part of two different ratios when we are comparing areas, and volumes have three different dimensions. So we would expect the a to the third compared to b to the third, since we were going to be then working with our three dimensions. Okay, so let's go ahead and try a few examples to see how this all works. Example 1, identify similar solids. Tell whether the solids in part A, this is part A, and part B, here it is, are similar to the solid shown in blue, this one. Okay, well, let's do the math to find out. I have gone ahead and labeled all of the lengths, widths, and heights so we know what corresponds to what. So we're going to take a look first at our length 1, our blue figure, and compare it to the length of the figure in A, and that compares 4 to 8, which reduces down to 1/2. What about their widths? Well, the widths compare 2 to 4, and here I'm showing that. The width 1 to width 2, 2 to 4, which reduces to 1/2. So far we have the same lowest terms ratio. And then the height, well, both of the heights are 2, so height 1 to height 2 is 2/2, and that's equal to 1/1, and that's not the same ratio as the first two. So we're going to conclude that they are not similar solids because the corresponding sides are not all in the same ratio. We have two that are the same, but one's different. They'd all have to be the same for the figures to be similar. Same shape, in other words, and they're not. Okay, what about B and our blue figure? Well, let's compare the lengths. Length 1 to length 2, we'll just go with the blue one first. 4 to 6, that reduces to 2/3. Comparing the widths, 2 to 3, that's already fully reduced. These are the same ratios so far. And let's see, what about height to height? Well, the height of the blue, 2, to the height of the Part B figure is 3. It's already fully reduced. All three of the ratios comparing all of the dimensions of this rectangular prism are the same. So we have two similar figures here because the corresponding sides are all in the same ratio. What about example 2? All right, in this one we're going to use the scale factor to find the surface area and volume of a figure. We are told that we have two, and they're showing us cans that have some food in them in the book. The scale factor of the cylinder shown is 87 to 100. So we have a small can of food and a large can of food, and their comparison is, when it comes to a one-dimension comparison, 87 to 100. And then they tell us the surface area and the volume of the little can. And from that, we are to figure out the surface area and the volume of the big can. All right, so let's go ahead and work that out. Surface areas compare, surface area 1 to surface area 2, they compare with a squared to b squared. Well, our dimensions here were given as 87 and 100, so that is our one dimension that we're working with. We need to square that, so 87 squared over 100 squared would be equal to the surface area of the first one compared to the surface area of the second can, which is our large can. So 87 squared over 100 squared equals 51.84 over our variable surface area. And we simply solve that proportion. You use cross products is a pretty easy way. So S, this is not 5, S times 87 squared equals 100 squared times 51.84. So the surface area will be 100 squared times 51.84 divided by 87 squared. Throw that all in your calculator and you'll find the surface area of the big can is about 68.49 inches squared, rounded off to the nearest hundredth. What about the volume of the large can? Knowing the volume of the little can. There's our volume of the little can. And again, the scale factor from the little to the big can is 87 to 100. So volumes compare. Volume 1 to volume 2 is equal to a cubed to b cubed. So we find the one-dimensional scale factor, 87 to 100, and we're going to cube that. So 87 cubed over 100 cubed is equal to 28.27 compared to the volume of the big can. So it's little can to big can, little can to big can. But again, the volumes compare with cubes. All right, let's solve this proportion. So we have V times 87 cubed using cross products equals 100 cubed times 28.27. Divide both sides by 87 cubed and you have the volume is 100 cubed times 28.27 divided by 87 cubed. And put all of that in your calculator, key it all in, and you'll see 42.9307, blah, 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 and round that out to the nearest hundredth. That's 42.93 inches cubed. So notice that when we figured out our surface area, we used inches squared. The volume would be inches cubed. Alrighty. Example 3, last one. Find the scale factor knowing the volumes of two similar figures. We have pyramids here, and we're told the pyramids are similar. That's given information. And we are to figure out the scale factor, which is comparing the dimensions, any dimensions of the two pyramids. So we're just picking this dimension here, the side length here from the top down to the base. So those are corresponding sides. We want P to Q. And we're told that the volume of the big pyramid is 1,000 inches cubed and the volume of the little pyramid is 216 inches cubed, which is very, very convenient for us. They both happen to be perfect cubes. All right, so we set up our proportion. Volume 1 is to volume 2. The volume of the larger pyramid is 1,000 compared to the volume of the smaller is 216. And the volumes compare with the side dimensions a cubed to b cubed. All right, so to figure out what our side dimensions are, and we're using P and Q for those side dimensions, we are going to take the cube root of both sides. Cube root of 1,000. What multiplies against itself 3 times to make 1,000? The answer is 10. What's the cube root of 216? What multiplies against itself 3 times to make 216? The answer is 6. You can find that information in your calculator by taking 1,000 to the 1/3 power and 216 to the 1/3 power. That will give you these pieces of information. They are nice, perfect cubes, though, so you can go ahead and just think those through as well. And the cube root of a cubed is a, the cube root of b cubed is b, so there's our P to Q right there. So how do the pyramids scale factors compare? P to Q, 5 to 3. And so there's your scale factor, 5 to 3. All right, that concludes the guided practice for this lesson. It's time for you to begin working on the homework, and we'll see you next time.